Okay, welcome guys, welcome back. So yeah, let's just get started from where we left off. And yeah, so we're done with design simulation, and so it's time to go for the layout of the common source amplifier with current mirror active loads. So again, yeah, so we're just going to be focusing on just this for the layout. So what I'm just going to do it first, I just need to prepare the design for layout. I can't just send all this forward for layout, so like I can send everything here on this window. So I just need to get the main design, like clean it, make it ready, condition it for the right layout form, yeah, then format, then yeah, we'll go ahead and do the layout. So to get this design ready for layout, I just need to create another scheme tab. Then all I just need to do is just try to copy the old design, so C for copy, then I move it to the new tab. So it's too big, it's too zoomed in, so let me zoom out. Okay, we're here. So again, it's all about the design for the layout. So all these labels here, I'm talking about the what's it called, that all these get value symbols for operation point analysis, or for the DC point analysis. We need to remove them. They are simulation symbols, so they need to all be removed. So removing them. So let me see if I can select the routing at once. Then okay, yeah, so I think, yeah, that's all removed. So next thing, again, it's just like want to do layout for the amplifier itself. Remember, I said it in previous video that if you're to circle out the amplifier like out of all the design, I said this, what makes up the amplifier is just transistor 1, 2, 3. This current source necessarily does not, like, it's not if you remove it, you can't say this is no longer a common source. Remember, I said that's the advantage of putting it here, and that's why it's practical. You get done it being here, anything that it's here should be part of the amplifier. So putting this current source here, you make it part of it, and since this is not already available, you want to say fabricate, you need to use other things to fabricate, so it will not be fabricatable and all. So we bringing it here and all, we make the amplifier less dependent on this, such that we can just use an external biasing for this, the amplifier. So this really not like part of the amplifier. So what we're going to do with that, I'm coming, give me some time. Okay, so then that means we're going to remove this to be removed, and yeah, so I just delete this, and so next thing we need to the pins here, you're seeing the VDD pin, the Vout pin, the VIN pin, and even this ground pin. Would have to replace it with another kind of pin. So we need to replace this as ports. So yeah, to do that, you again hit the insert button, and yeah, just go to a scheme, then check for I can't remember the name. Let me just search for pin. So good. So IO pin, in pin, instead of this generic label pin, we are going to be using O pin, that's output pin, or I pin, which is input pin, or we use the IO pin, that's the input output pin. So depending on the kind of ports we have. So let me just go ahead first and choose this IO pin, and so where can this IO pin be used? The IO pin will be used to replace this pin, this VDD pin. Why? It's IO it's input output, and it's a bidirectional pin, so you use it to replace ports that are bidirectional. So your supply port is bidirectional. It's not like it's input or output, it's just input or output, like it's by input and output at the same time. It's bidirectional, so that's why it's being replaced with this. The VDD will be replaced with the IO port. For the output will be, this VOut will be replaced with an output port or pin, because it's output, it goes out, that's the direction it goes. While the input, it goes in, that's the direction it will be replaced with the input pin. Why the ground is also a power supply port, right? So it's still going to be replaced with IO pin. So I'll just make a copy of this. So IO pin, then okay, wait, let me move the ground. Okay, think oh no. Sorry about that. Copy. I think because this is not aligning with the grid, so just having issues like aligning it. So let me just try to adjust this. let me quickly just readjust. So all is well arranged. So let me label this pin, this port here. So I would call it VREF, the reference voltage for the current mirrors here. Yeah, so yeah, we're done with the naming of the ports. Then next, I think we're almost ready for layout. We're almost ready. So let me save. So S, and let me call it CS EEE 352. 352. I already have 352. 352. Let me just call it sim, for like symbol. If I wanted to make a symbol, this is symbol, I just need it like the form in which I need the amplifier to make it a symbol. So that's why I'm just calling it sim. So saved. So let's do one more thing. So you come to this point, LVS. So LVS, you click. So LVS netlist top level is a sub circuit. So I'm going to be ticking that. I'm going to be selecting that option. So let me just confirm it's selected. So it's selected. So let's just save, then generate the netlist. So let's be sure the netlist has been generated. No, sorry. Show netlist after netlist command. So show netlist. So we have this. Maybe in case you're wondering why I had to do this, let me untick it. So unticking, then let's view the netlist again. Like this is what you have. You can see this. You just have the list of components. You're listed out this way and all, but let me do this again, then generate the netlist. So all those has been, like, all this information has been hidden. Like, so each of these guys, M1, M2, they are seen as like a sub-circuit. So I think it's important for that layout, and we want to also do the layout as a schematic. So you just be comparing each devices as like a sub-circuit. So it's more of like compress the content for you. So yeah, I think then we are done here. Then next we'll go ahead to launch Magic for your layout. So I'm using Magic for layout. So problem. Oh, sorry, that's a mistake. Okay, so just go ahead and call Magic. Just one. Okay, so we are here. Again, this GF180 Magic devices. Maybe for Skywater, slight difference, I know, but we're still just good to do the basic thing. Okay, so now, so we'll be focusing on Magic for now. So we are done with, I think for now we're done with a scheme. So first thing, there are two ways, basic method to do layout. There is Netlist-driven layout, and there is the pixels. So that is, you can either go by generating the pixels, like I select the cells from here. So NMOS, in that common source design I have 2 PMOS and 1 NMOS. So I'll just go select 1 NMOS, edit the sizings and all, do the same thing for the PMOS, edit the sizings and all. So that's pixel like based layout. But you can do spice driven, netlist driven layout. So that's what we're going to do here. It's much easier because all Magic will just do for you, it import all the devices for you, and you just have to just start with routing or wiring, unlike the pixel based where you'd have to start bringing in the components yourself before you now start wiring. So it's a good advantage for cases where the designs are quite complex. You have more than 3 transistors, even more, so you just import everything all at once. Okay, so that's a good feature Magic can give. I think for K layout, a good feature similar to that, it's would I call it the text based layout or the programming based layout? So you can write Python scripts to generate your cells and all. So yeah, so let's just move on. Let's start. So to do that, you come here, file, click on file, then you get click on import spice. So import spice. So the spice you want to import would be in, let me give you an idea, would be in, go to your home directory, home, and there to be in this folder, this .scheme folder. That's where the spice netlist we're looking for would be. So let me confirm here. You'd see it here. So that's CS352, not this one, 352.spice, not this one, is this one, 352 symbol, symbol.spice. So that's what we're looking for. So that's what we're going to go to. So I'm in designs, I need to go back to my home directory. So home directory, then look for the .scheme folder, and here simulation, then we're looking for CS E352, so this same spice. So open, so you can see everything imported already. So let's get started with layout. So let me zoom in. What's going on? Okay, I think Z is just for zooming. Z for zooming, unlike Escape. Shift Z, then Shift Z is for zoom out. So let me just select, let me separate. I can see I already have DC DRC error like of 10. So I think one of this error may be due to having this devices packed together. So let's just separate them. So I want to separate this device. I'll just keep the cursor over the device, then press the I button, I on your keyboard. So I to select the cell, then move, M for move. So move. So that's been moved, and you can see my DRC reduced already. Then so I want to separate these two devices. So you can see there are two devices. So I just place my cursor over one of the device, then each the I button, then next, I move to the position I want to move it to, then I press M. So 0 DRC. So okay, so of course we're expecting 3 devices, and here we have 3 devices, and these are the ports we created. So good, we have our ports. So good. Next, though, would have just gone ahead to, by the way, let's identify our devices. So from here you can see these. Let's see. So if you want to be able to know which is PMOS, NMOS, so it's the color scheme, just come here. Let me also refresh my memory. So you come here, check the devices. So N transistor, P transistor, so that's the same thing as PMOS, NMOS, PMOS. So N transistor, the NMOS, has this brown background with this green stripe that are slants. So you can see that corresponds to this device. So this is the NMOS. Then you see the PMOS, that has this red background with would I call it off-white stripe slanting to the other side. So you can see it's definitely this. So yeah, so these are PMOS and these are NMOS. So good, we've been able to do the identification. But there's one issue here. It's not really an issue there, of course. It's not an error, it's not like it's an error, but if you check the sizing of our devices, like you can see this is pretty big, it's too long, it's too wide, it's the width. Remember from our design, we got for the PMOS, we got width of 85.6 micrometer. So that's pretty long. Maybe the length is fine, we don't have to tamper with the length. The length is okay. I think the last time I used GF 180, when I went beyond 0.8, I think there was issue with that. So because of spacing of the materials, so I think 0.8 is just maybe okay for now. If there's issue with that, we may move it to 1 micrometer. But this 85, but remember, whatever you do to the sizing, whether you change the width or you change the length, ensure the whole aspect ratio is constant. The aspect ratio is constant, that is the ratio W/L should be constant, even if you want to change either the width or the length. But again, we're not touching the length. So back to this. So there is issue with the width. It's too long, it's too, I mean, for the cases where you're concerned about the chip area, the size of the chip, this is already a problem. How much more if we have more devices to fabricate together? So this is already getting big, you know. So a way, and also maybe issues with parasitics and all. When you're having big width like this, you know, you have parasitic capacitances and all that. So we may want to not reduce the width, but split the width, so that instead of having just one single device with long width or wide width, you have parallel devices with shorter width. So when you have devices in parallel, it's just a concept in layout, and which I think for your classroom learning you may have come across. The concept in layout where you one device can be made to be equivalent to more than one devices in parallel. So that's the concept we're going to use here. So we want to reduce this. So that concept is the concept of multiplicity, or number of fingers in layout. So we'd have to reduce this width, it's too much. I think also we can do that for the NMOS. Yeah, it appears 22 micro too it's too wide also. So that is, when we try to split each devices into smaller parallel devices, the minimum should be less than what am I saying? The maximum we get, the maximum possible we get of that splitted devices should be less than the maximum, which should be less than 20, because already we can see 22 is still long, so we just have to go below that. So maybe 10 will be fine, because 22, then it's almost like half of this. So looking at it, half of this would be around here. So I think this is still good. It's still good to work with. So we can just split this into two parallel devices. So 10, 10, or 22, 11, 11. So it's good. At least I have the entire, if it's 11, which is maybe from here to about here, I can have the entire width on the screen. I can view at once. So we can just go with that. Though for real application, we will have to still split it maybe up to 5. So how do we do that? So we just have to go back to a scheme, and do the sizing. So but before then, let me just check how much time we've used. So I'm just going to stop here, so I'll continue in the next video. Thank you.